Welcome to Ganit Nidhi. Today we will look at what are known as Stirling numbers of the second kind. These are named after the 18th century Scottish mathematician James Stirling. We can define Stirling numbers of the second kind in two ways. One, the number of ways in which n distinct objects can be divided into r identical boxes with the condition that none of the boxes is empty. Equivalently, we can give an alternate definition. The number of ways in which the set of numbers s, which is natural numbers from 1, 2, 3, so on till n, can be divided into r blocks such that each element of s belongs exactly to one of the r blocks. This is how we usually denote these numbers s and r, or within curly braces n over k, and we pronounce this as n subset k. Let's look at a few examples. Let's calculate 4 subset 2 considering the set 1, 2, 3, 4. Now this can be divided into two blocks in the following ways. Sets with sizes 3 and 1. So one set with size 3 and the rest the other set with 1. So there are 4 such cases. And then sets with size 2 and 2. And you can see that there are 3 such possible cases. Thus the total would become 4 plus 3, and 4 subset 2 would be 7. Now consider another set 1, 2, 3, 4, and we will calculate 4 subset 3. This can again be divided into 3 blocks in the following ways, and thus 4 subset 3 would be 6. Let's look at a few properties. If the number of elements are less than the number of boxes we want to put them in, there is no way to do that. So n subset k, where n is less than k, will be 0. If we just have one box and a non-zero number of elements to put them in, there is no way to do it. There's only one way to do it. That is, we put them all in one box. So n subset 1 will be 1. Similarly, if there are n elements and n boxes, we just have to put one element in each box, and thus there is only one way to divide these n elements. So n subset n will be 1. If there are no boxes available, the number of ways one can put n elements is 0. So r subset 0 is 0. Similarly, if there are no elements and non-zero number of boxes, there is no way to do this partition. So 0 subset n is 0. And by convention, we say that if there are no elements and no boxes available, the number of ways to do this is 0. So 0 subset 0 is 1. Now let's calculate n subset 2. Let's consider the set 1, 2, 3, so on till n, and we take its first element, that is 1, and put it in one of the two target boxes. That leaves n minus 1 elements, namely 2, 3, so on till n. For each of these elements, we can choose to put it in the box containing 1 or in the other box. So there are 2 options for each element, and in total there will be 2 raised to power n minus 1 options. But remember, we've overcounted, because this includes one option in which all the elements from 2 to n, they are put in the box containing 1, which will leave the other box empty, which is not allowed. So we need to take this particular case out, and so n subset 2 will be 2 raised to power n minus 1, and from there we take out 1. Now let's establish a recurrence equation for n subset r. Again, let's consider elements 1, so on till n, and we want to distribute these into r boxes. Now we consider 2 disjoint cases. The first case is when the element, let's say 1, is in a box by itself, and the other case is when the element is not alone but with some other elements in some box. So the first case corresponds to choosing the remaining n minus 1 elements, and from there we put them into r minus 1 boxes, because remember 1 is in a separate box. And in the second case, let's keep 1 aside for a second, and we distribute the remaining n minus 1 elements, that is 2 to n, into r boxes, and then choose which of these boxes to put 1 in. So n minus 1 subset r is the number of cases for the former, and n is the cases for the latter, and we multiply these two numbers to get n multiplied by n minus 1 subset r, and these two being disjoint cases, we add them up and get a recurrence equation for n subset r. Now let's try to calculate a few values for n subset r. Now remember, we have this convention 0 subset 0 is 1, So let's put that in. Now if the number of boxes to distribute numbers are 0, we get the number of ways to do that as 0. So n subset 0 is 0. If the number of boxes is 1, we get only one way to distribute n numbers. So n subset 1 is 1. And if the number of boxes are more than the numbers that there are to distribute, there is no way to have this partition, and we get 0. If the numbers to distribute and the boxes are same, again, there is only one way to do this partition. That is, we put one number in each box, and the number of ways to do this is just 1. Now let's calculate n subset R for a specific case, that is 6 subset 4. Now remember that recurrence equation we talked about earlier. So we need to add up the numbers 5 subset 3, which is 25 in this case, and add that to 4 multiplied by 5 subset 4, which is 10 in this case. So 10 multiplied by 4 plus 25, and we get 65. Now let's calculate n subset n minus 1. Again, let's consider the case of a set 1, 2, 3, 4, which we want to partition into 3 boxes. This amounts to choosing 2 elements which would need to be together. All other elements will need to be put alone in other boxes. So we can do this in 4 choose 2 ways. That is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Thus the partitions will be these, and we get these 6 cases. So, and we can generalize to say that n subset n minus 1 would be n choose 2. Now let's calculate n subset n minus 2. Again, we consider the set from 1 to n, the natural numbers. We want to distribute into n minus 2 boxes. Again, let's consider 2 disjoint cases. There is a box which will have 3 elements. The rest will have 1 element each. And the second case is there are 2 boxes with 2 elements, and the rest will have 1 element each. Now case 1, we basically is about choosing 3 elements from n elements. So that is n choose 3. And in the second case, we have to choose 4 elements first. And out of that, we need to form a partition of 2 sets of 2 elements each. So we choose n choose 4 to choose 4 elements. And then let's say these elements are A, B, C, and D. These can be further partitioned into 3 cases in which there are 2 sets, in which the set size is 2, and there are 2 boxes. So that's 3 ways. So that amounts to saying that n subset n minus 2 would be n choose 3 plus 3 multiplied by n choose 4. Now let's calculate n subset 3. Now let's recall the identities that we've established earlier. We have n subset 3 is equal to n minus 1 subset 2 plus 3 multiplied by n minus 1 subset 3. And again, we calculated n minus 1 subset 2 earlier. So we get this number equal to 2 raised to power n minus 2 minus 1, and Sn subset Sn comma n would be 1. Now we put the value of Sn minus 1 comma 2 in this first recurrence equation, and we slightly simplify it, take an expression to the other side, and it's a fairly straightforward recurrence equation. You solve that, you basically get you have to sum up these geometric progressions, and you can simplify this to get this expression as the value of n subset 3. And this is the summary of all the properties that we've discussed. Thank you for watching. Hope you enjoyed seeing this video, and if you did, share this video with your friends and subscribe to this channel.